the way I started this in second period, and then of course in third, is I wanted to do a brief review. I'm going to put everything in one place. I will not say anything that I have not already said, okay? So I want to start with a brief reminder that I have given you quite a bit of vocabulary. And most of that vocabulary centers around these 5 symbols. Would you guys agree with that? Now, for the most part, I've not taught you very many things that are new, except in relation to these 5 symbols. The first symbol is displacement. If your notes are complete, then you know that displacement can be written as x final minus x initial. You'll also note that this is a vector quantity. Good so far? Do you also remember that displacement is change in position? And can be determined by finding the area of a velocity versus time graph. You guys remember all of those things? All stuff that we've talked about in here. Now, these two are both velocity, but I have initial and final velocity. What's a little bit of subtext is the only way that that can be true if they are both considered instantaneous, which I did not leave myself enough space to write, so I will have to adjust. Instantaneous, there, velocity. They too are vector quantities. By definition, velocity is a rate. The rate of change of position. And because it's a rate, it's basically the change in position over the change in time. Writing it like this because we've also talked about the fact that it is the slope of a position versus time graph. And if that slope is changing, then the velocity is changing. Still nothing new, right? Acceleration. Perhaps newish. I'm having to break your definition and insert mine. You guys want it to mean speeding up, but it does not. It is a vector, though. It has direction. That part's been tough for some of you, and will continue to be so for a little while. But it is defined as the rate of change of velocity. Therefore, it is a rate, delta V over delta T. You can't really use these. I'll remind you, it's hard to use these. You can only use these if your function is linear. I'm saying this because they are symbols of slope, right? Delta x over delta t and delta v over delta t are symbols of slope because acceleration is the slope of the velocity versus time graph. So although this is vocabulary, you understand that there's a lot here. Like, I can't just make an index card where you flip it over and there's one thing to read. It'd be an index card with 1, 2, 3, 4, 5 sides, perhaps. That's a hard index card to make, right? But you need to know all of these things. They are all definitions of each of our terms. Time I don't really have to define too much for you, but I do think there's an issue that we're really referring to the time interval where there exists a constant acceleration. I write it like this because if the acceleration changes, that instantly starts a new time interval. Now, there's more. In fact, we looked at a whole bunch of graphs, and didn't we generate more things? Right, those were generated by looking at those graphs. I say that because we do have a set of motion equations that are related to these 5 function variables. And there are more than just these. We generated these in class by doing a little bit of work on some graphs and then algebra, correct? In fact, V equals AT plus VI, and delta X equals 1/2 T plus VI plus VF are just slope and area, right? That's where those came from. I say slope, but this is y equals mx plus b. In addition to that, we combined these and created a new one. And I know you're writing it down, but this is all what's on the right-hand board. Right, we got this by just combining them, right? Nothing new there. So all this seems like old news, correct? Good. So what I'm about to ask you to do shouldn't be too hard. I want to ask you a few questions about this. Assuming you've been paying excellent attention, what I'm going to ask you here should be straightforward. Everybody sees what kind of graph this is, velocity versus time graph. I'm going to plot something on there so that we can kind of observe it. Oops. There we go. Does everybody see the graph okay? Can read all my points okay? I have 2 questions for you. Can you tell me how fast this object is going at the 10-second mark? And can you tell me how far it's traveled during the 10 seconds? Nothing new. We've done this before. Try, please. Do you see why we have a problem? Okay, we have a problem. Let's handle the problems. Let's start with just that piece of information, whether the object is speeding up or slowing down. I'll point out at time 0, the object has a velocity of -2 meters per second. So the negative direction, can we call that backwards for now? Yes. Okay. How fast is it going here? Is it faster or slower than 2 meters per second? Slower. I think it's slower, right? The number would be a number that is less than 2. Agreed? Yes. Is it still traveling backwards? Yes. So can we agree that it is now traveling slower? I know the acceleration's positive. That's not what I asked. I just asked if it's speeding up or slowing down. How fast is it traveling here? 0 meters per second. So in the first 4 seconds, it went from going 2 meters per second to going 0 meters per second. That's slowing down. Agreed? Yes. The acceleration is positive. No doubt about that, because the slope of the line is positive. So your first misconception, that I believe we can say I clearly highlighted is you would like the acceleration to tell you if an object is speeding up or slowing down. Do you now know that it doesn't? These are notes, right? These are things you should write down because you don't know these things. But here, I'll sum it up for you. A positive acceleration means the velocity becomes more positive. That's all it means. A positive acceleration means the velocity becomes more positive. Look, I understand this is a different way of thinking, and you've been conditioned with your own vocabulary and your own ideas in math. And all of the strategies you've been given to figure stuff out in math doesn't work if you never understood it in the end. So I'm not trying to be cruel, but this graph clearly has a positive slope. You would love positive acceleration to mean going faster. That's not how it works. Positive and negative is a direction. So it has an acceleration in the positive direction, but the object is moving in the negative direction to start. Remember, we put the thing on the track. So the object's going backwards, but the acceleration is forwards. Do you understand? Now, eventually, the object does stop and then starts proceeding in the positive direction. So everything on the left side of the line, it's slowing down. Everything on the right side of the line, it's speeding up. But the acceleration is the same value the whole time. All good?
Yes.
Look, if you throw a ball in the air, on the way up, is it speeding up or slowing down? And then it comes back down. On the way down, is it speeding up or slowing down? What made the ball come back down?
Gravity.
Did gravity change?
No.
No. And in fact, you made this graph with your gravity lab, correct? So you know what this looks like. But do you see how easy it was to fool all of you? So I hate doing this. I hate what I'm about to do. I don't hate myself, but I hate doing this. I hate rote memorization because you don't learn anything. You learn facts. But look, or you end up knowing facts, but it's just dumb. But Excel, velocity, result. Okay? If the acceleration is positive, but the velocity is negative, am I speeding up or slowing down? I mean, that is what's pictured right here, right? As what we've just been talking about. If my velocity is negative, but my acceleration is positive, we are slowing down. If my acceleration is positive and my velocity is positive, are we speeding up or slowing down? Speeding up, that's this part of the line. I'm speaking to what's right in front of you. I know I have, unfortunately, shaken your confidence, but I'm just having you repeat yourself. Speeding down? No. The heck? Speeding up. If the acceleration is negative and the velocity is positive, am I speeding up or slowing down? Slowing down, that's right. Right, my acceleration is backwards, but I'm moving forwards, that would slow me down. But if my acceleration is negative and my velocity is negative, am I speeding up or slowing down?
Speeding up.
Speeding up, sure. You got a chart, right? I would rather you be able to figure it out. And you should. But now you got a chart. Am I going to catch you? I'm going to catch you still. I'm still going to find you. I'm still going to find the people who don't get it. But at least this will help. It'll help get you started. And you can just look at the graph. Every time passes, this object is getting to be a smaller velocity, a smaller number. But as time passes here, those speeds are becoming bigger and bigger numbers, right? All right, so we haven't even gotten into the questions I asked. Like, how fast is it going at 10 seconds? Let's see if we can figure that one out next. That's going to be my favorite. Are you ready? Because what kind of function is this? What does it look like to you? Linear. y equals mx plus b. Except not y equals mx plus b, right? Because we have different symbols we are going to use here. And we've done this translation already, correct? Except the slope of the line, that's the acceleration. Can you find the slope? Right, you guys can do slope. You've passed Algebra 1. I checked. I've looked at everybody's math scores. You have passed Algebra 1. What is the slope of this line? Let's be confident in our answers. Say them out loud. It is 1/2. Rise 2, run 4, correct? So 1/2. What is the initial velocity of the object? What is the y-intercept? -2 meters per second. This function tells me the velocity for every moment in time. What time am I interested in knowing the velocity for? 10 seconds. Am I asking very much? No. And you probably could have figured this out a different way, right? Isn't it true that every 2 seconds the velocity changes by 1? Isn't that what's happening here? So after 4 seconds, when I go to 6 seconds, it's got to be at 1 meter per second. And at 8 seconds, it's got to be at 2 meters per second. And at 10 seconds, it has to be at 3 meters per second, 5 minus 2. Wow. So, yeah, you heard about second and third period, huh? All right, good. My recollection, and I hope yours too, is that there's a way to figure out the displacement of an object if you have the velocity versus time graph. I bet it's over here someplace. Somebody want to say what it is? Gotta hurry. Got 14 minutes. It's over there. You wrote it down. Do I need to put it on the screen again so you can tell me? How do I find the displacement from a graph? Go ahead. Yeah, except I don't have either of those. There's no position information on this graph. I need something else because I have a velocity versus time graph.
Area of velocity over time?
The area of velocity versus time. The area of a velocity graph is displacement. That's where the second function came from, right? So I'm going to look at this and see if we can do it. I'm looking at specifically this area. Have we done this before? Did we do the area of a triangle in here? Yes, we did. But I'll even give you one more than that. We formed a function out of that. Doesn't that look familiar to you in some way, shape, or form? Let's consider the first 4 seconds. 1/2 times 4. What is the initial velocity in the first 4 seconds? -2. That's the initial velocity at the start of those first 4 seconds. What is the final velocity for those first 4 seconds? 0. How far does it go? 1/2 times 4 times -2. How far is that? This is hurting my heart if you can't do this. Maybe you need a calculator, but I will laugh at you if you use a calculator to do 1/2 times 4 times -2. Thank you. -4 meters. So obviously in the first 4 seconds, the object went backwards 4 meters. So you're saying all that stuff we did last week and the week before, none of it stuck. So I ask you, can you tell me how far it went in the next 6 seconds? What's the time interval from 4 to 10?
6.
What's the initial velocity at 6 seconds? What is the final velocity at 10 seconds? It's 3 though. I don't know why I wrote 5. It's 3. Why did I write 5? I do not know. 9? 1/2 times 6 is 3. 3 times 3 is 9. So, my object traveled 13 meters. That's the distance. Strip off all the negative signs, just add up the numbers. But my object's displacement seems to be positive 5 meters. It's 5 meters in the forwards direction. Wow. So, again, nothing new here, right? Is there anything new here? I'm about to do something new. I said I would do it at the end of class. I have 10 minutes. So first, you're looking at test questions. This is what your test will be. And there's nothing new here. I have not brought anything new to this. Clearly you need practice, and that's what I'd hoped we were going to do today. But I also tried to put this in your hands. You created these graphs, right? You played with the cars on the track. You had an opportunity to make this in front of yourselves. Am I wrong? And that's what I tried to do with our laboratory work. I think we're missing some of the connections here. But I do want to ask something of you. And I don't know if I can go this far. This might be a bridge too far. You guys are creatures of habit, and you are used to just believing things are one way and one way only. So are you willing to step outside of that for a minute so I can show you something? And I don't know if you can take this journey with me or not. We'll see. I want you to be more capable though, okay? Euclid's geometry is something that you are trapped in. And Euclid told you that that's a trapezoid. That the rules for a trapezoid were 2 parallel lines and 2 anti or non-parallel lines. Correct? And that's what I've just drawn here. Everybody good? Well, there is something called non-Euclidean geometry. Euclid's geometry says things like parallel lines will never meet. And a polygon has to have enclosed space. But there are rules, and there's also other sets of rules. Like Euclid's geometry wouldn't allow for a negative area. Areas are positive because they exist in real space. But Euclid didn't deal with vectors or symbols the way we do. Our areas represent physical motion, correct? And we clearly have situations in which our objects travel in both a positive and a negative direction. So what if I told you that in non-Euclidean geometry, I can take 2 parallel lines and 2 non-parallel lines and make that. Isn't it still just 2 parallel lines and 2 non-parallel lines? You wouldn't call this a trapezoid because it has an occlusion in the center, right? The enclosed space, it's changed. But can you imagine if this were something I had that was real, made out of fabric, and I'm holding it and I just folded it? I'd go from the top to the bottom, correct? It's like a sunshade. You guys know what I'm talking about, those sunshades that you fold first and you kind of cram together? Well, that's what I've done here, but by folding it, I created an area of negative area and an area of positive area. This is a trapezoid in non-Euclidean geometry. It's just a trapezoid. All the rules of trapezoids still work. And I hope that there's a group of you who are seeing why I might be interested in that trapezoid. Are you seeing why I might be interested in that trapezoid? I would like you to do this. I would like you to walk in this journey with me just a little bit further and realize if that's a trapezoid, then the area of a trapezoid should still work. Isn't this the area of a trapezoid? The difference is I've got a negative side and a positive side, but my displacement should still be the same. The rules should work. So let's see. What's the entire time interval? 10 seconds. What is the initial velocity? Base 1. -2. What is the final velocity? Base 2. It's 3. 3 minus 2 is 1. 10 times 1 is 10. Half of 10 is 5 meters. Do we see that it works? So first, I want to tell you that our second equation up there, it will give you the displacement, even if the velocities are positive and negative. It works just fine, but it gives you the entire displacement. Now, if you're trying to take notes, it gives you the entire displacement over the interval. It can't tell you the partial displacements unless you break up your system into partial displacements. Meaning, there's no way I could get to 13 meters without knowing the two individual areas. Do you see that? I can never tell you how far the object went, its distance. I can't tell you that from this. But I can certainly tell you the entire displacement. That's clear. Now, we've come a long way, haven't we? There's 4 minutes left. Can you make a position versus time graph that would represent these same events? And when I ask you this, I want you to realize if we're using the detector, wouldn't we have to start in front of the detector far enough away so that the object can move backwards and not hit the detector? So where should my initial location be? How far in front of the detector should I start? How far does it have to move backwards? -4, I believe. Right, isn't this area -4? So I need to start the object at the 4 meter mark so it can move backwards 4 meters. So we don't have much time, but I believe we have enough time. By the way, who has a TI calculator? Take it out, put it in front of you. Hurry, we have 3 minutes now. Now look, I'm going to talk a little bit quickly here because I want all of this to sink in, but we're going to start at the 4 meter mark. After 4 seconds, we know that we are stopped. That's an important point, right? We turn around there. And then at 10 seconds, we know that we are going to be further away now. We're going to be at the 9 meter mark. Right? We went backwards 4 and forwards 9. And at time 0, our velocity is negative. So the slope of our graph should be negative. At time 4 seconds, our velocity is 0, so our slope should be 0. And at time 3, our velocity is positive, so our slope should be positive. Can you connect these with a smooth curve? Still nothing new yet, right? Except this is new. Delta x equals 1/2 a t squared plus vi times t. We talked about that yesterday and the day before. X final minus x initial equals 1/2 a t squared plus vi times t. Correct? Nothing surprising there. X final equals 1/2 times 0.5. 0.25 t squared plus vi -2 times t plus x initial plus 4. You guys have calculators, right? Hit the y equals button. Put this in. Y equals 0.25 x squared minus 2x plus 4. Or you guys know what I'm telling you to do, right? You got those calculators, are all fancy. You use them. Put it in. You see, your calculator will give you your answers. But of course, it has to be y1 equals 0.25 x squared minus 2x plus 4, because your calculator is stuck in y and x. Then hit zoom standard. Doesn't it produce the right parabola? Doesn't it look just like this one? If not, practice. Look, we've come a long way. It's the end of the day.